Good morning, students. Welcome to Commutative Algebra live lectures. In this lecture, we'll discuss about integral dependence. Okay, so let's start with what is meant by definition of integral dependence. So take B, which is a ring, and A, a subring. Okay, then we say that an element X belongs to B is integral over A if X satisfies an equation of the X satisfies an equation whose coefficients are coming from A. That means x power n plus a1 x power n minus 1 plus and so on an should be equal to 0 for some n and ais belongs to E. So this expression should be equal to 0. Then we say that B is integral over A. Okay. We can quickly see some examples that every element A over A is integral over A, because if you take this polynomial x minus A, this is clearly in A of x. When you substitute A here, you get 0, right? So every element of A is integral over itself. If you take Z, which is a subring of Q, then we will see what are all elements of Q which are integral over Z. Okay, we'll prove that. So take some x, which is a rational number r by s. Okay, and we will take in standard form. That means r upon s is 1. Okay, then if at all, suppose if this number is integral over z, that means there exists n and ais belongs to z such that this expression is equal to 0. Okay, now if you simplify this and keep going, r power n, you can make it, because remaining all terms s is common, so s into minus a1 r power n minus 1 and so on. So right hand side, whatever you have here, this right hand side, s divides right hand side, so and that implies s should divide r power n, but s and r, they don't have any element in common, so therefore s only possibility is s should be equal to plus or minus 1. That shows that our initial x is equal to r upon s belongs to z, because s is plus or minus 1. So what we have observed here is that the only elements of q which are integral over z are nothing but integers. Okay, so if it is a non-integer, a rational number, then it is not integral over z, right? Okay, now we'll discuss some characterization of integral elements. Okay, so the following statements P, F, A, E means the following statements are equal. There are 4 statements. So first one is x is integral over A is same as saying that this A of x is finitely generated A module. That means finitely generated over A. And it is same as saying that ax is contained in C, ax is contained in C, which is a subring of B, such that C is integral, C is finitely generated over A. Okay, so you can see here this like this. Okay, so C is finitely generated over A. And the fourth one is that there exists a faithful AX module M. So M is AX faithful. What is meant by that? We say that M is A faithful if annihilator of M is 0. That means other than 0, no other element kills M. Okay, which is a finitely generated A module. So we want to that M is finitely generated A module. Okay. So what are these 4 points? The first one is X is integral over A. The second one is AX is finitely generated over A. Is same as saying that ax is contained in a subring of C, which is finitely generated over A, and we have a faithful ax module M, which is finitely generated as an A module. Okay, proofs are not at all difficult. We'll just go through the main points. So we want to say, suppose 1 implies 2, we want to prove. That means if x belongs to B is integral over A, then we want to show that ax is finitely generated over A. Okay, that means we should able to find finitely elements here, okay, which generates entire ax. Okay, that is not at all difficult, because it is given to be x is integral over A, so we have an expression for some n and ais are coming from A, right? then you keep x power n here and put it all these things this side. Therefore in particular x power n is what? Minus a1 x power n minus 1 and so on minus an, right? Okay. And if r, so therefore x power n, what we should understand is x power n is minus a1 x power n minus 1 minus a2 x power n minus 2 and so on minus an. Okay, so xn is generated by xn minus 1 up to x naught, or 1 x1 x2. Then xn plus 1, we can observe that this can be generated using this, you just multiply by x here and take it here. So xn plus 1 is generated by x. So this is, you can call it, this is generated by x square up to x power n, right? Similarly x power n plus r is generated by these many elements. Okay, so it is, observe that if we have 1 x power n minus 1, then we can generate x power n, and once you have x power n, then using x up to x power n we can generate x power n plus 1 and so on. So any positive power of x we can generate using these values. That shows that a power ax is finitely generated over a module. Okay, and 2 implies 3 is obvious. What is 2? It says that ax is finitely generated a module. This, we have already something which is finitely generated a module, so simply take c as ax, then 2 implies 3 is very obvious. 3 implies 4. That means whenever we have this situation, we want to show that there exists a faithful ax module which is finitely generated. So take our m as c. So whatever we have here subring c, take that as our, so take our m as c, then because as c is finitely generated a module, m is already finitely generated a module. What is enough to prove? So our aim is to prove that this m, whichever c is, m is ax faithful. Okay, ax faithful module. That means what? We want to show that if we take any element here and multiply by that to m, if it is 0, then that element has to be 0. Okay, so we will take an element y belongs to ax such that y times m is 0, then our finally we want to show that y is equal to 0. If we prove that, then it is faithful. Okay, so that is same as proving this statement, right? Okay, so start with y times m is 0, right? Since this is because our m is c and c is a subring, so obviously 1 will be there in c, so 1 is also there in m, right? That means what is meant by saying y times m is 0? So y times any small m is 0 for all m in m. So in particular 1 is there in m, so therefore y times 1, which is y, equal to 0. So that proves that y is equal to 0. So therefore annihilator of m is only 0, no other element is there. That means m is ax faithful module, right? Okay, now we want to show that 4 implies 1. That means when we have m which is ax faithful, okay, ax faithful, then and m is also finitely generated over a, we want to show that x is integral over a. So our claim is what? Our claim is this x is integral over a. That means we want to show that this x satisfies some expression coefficients coming from a. Okay, this, because this m is faithful and finitely generated a module, we define a map, 5 maps from m to m by simply sending this given x m times x, so multiplication by x, right multiplication or left multiplication. Okay, and we take an ideal a as our ring itself. Okay, then we can check that this phi of m is contained in m. Okay, but m is same as this am because m is an a module. Okay, so therefore the result which we have discussed earlier, whenever phi of m is a times m, then this phi satisfies an expression of this form: phi power n plus a1 phi power n minus 1 and so on, a n is equal to 0, where these ai's are coming from a. But remember, whatever this left hand side, this is a map. Okay, so therefore when we say that some map is a 0 map, after every element is sending to 0. That means when you, just like f, we say that it is 0 if f of x is equal to 0 for every x in that coming from domain, right? So if we use that, then it is applied for every m, it should be equal to 0. And if you take inside this x phi n of m, phi n of m, because phi of m is xm, then what is phi square of m, which is phi of m. Okay, this is nothing but phi of xm, right? When x will come out, but m will go to again xm, so you get x square m and so on. So in particular, phi n of m is x power nm plus a1 and so on. So if we simplify this, we get this one, right? So therefore, if you take this as our y, element y, then we are getting y times m is 0, but we are in a faithful module, so that means that y should be equal to 0. That shows that x power n plus a1, x power n minus 1 and so on 0. So therefore x is integral over a, right? Fine. So we have just now proved the characterization of integral uh, elements, right? So what we have proved is that this x is integral, so of course x belongs to b, is integral over a is same as saying that ax is finitely generated over a. Okay, and this is same as saying that there exists a subring and there exists a faithful ax module and so on. Okay, as a corollary, we can prove it in not only for one element, for any finitely many elements. That means if xi's x1 x2 up to suppose xn, they are belongs to b, which are integral over a, then we can see that this a together with these elements, okay, this is finitely generated over a. Okay, for n is equal to 1, we have already proved this result. Then we can assume for mathematical induction, so for n is equal to 1 we have already done, so assume for mathematical induction true for n minus 1. Okay, then you can write this a of, the idea is very simple, a of x1 x2 xn, you write this as a of x1 x2 up to xn minus 1, then joining xn. Okay, simply this you take it as suppose b, then this is simply b of xn, right? Now this xn is integral over a, right? So in particular it is integral over this b also, right? So we are getting that xn is integral over a, this implies it is also integral over b, because b is nothing but a of x1 x2 xn minus 1. So whatever polynomial we have over a, that same polynomial we can work for a of x1 x2 xn minus 1. Now again applying by previous result, what we get is that b of xn is finitely generated over a, right? So that shows that so this is over b, but b is finitely generated over a. Okay, so by using transitivity for finitely generated, we get that b of xn is finitely generated over a. Okay, that means is same as saying that our b is a x1 x2 xn minus 1, so therefore this is finitely generated over a, right? So proofs are not at all difficult, we have to just use induction technique there and transitivity of finitely generated modules. Okay, fine. As another corollary, if you take this c, which is elements of b such that x is integral over a, then we can prove that this c contains a and which is a subring of b, so this is a subring. So if we want to prove that it is a subring, take any two elements, then it should be closed under addition, subtraction and multiplication, right? So take two elements x comma y in C, then because C contains all elements which are integral over A, so therefore x and y are integral over A, right? So therefore this A x comma y is finitely generated over A. That's now what we have proved from here, right? If you call it this as some s, so s is finitely generated over a. But if you observe that s is same as s of x plus y or x minus y, okay, or s is also same as s of x times y, because this x plus r minus y and xy, they both belongs to this s, which is a of x comma y, right? So therefore this one is finitely generated over a, that means this element is integral over a. Similarly this is finitely generated over a, so therefore what we can say is that they are integral over a. So but whichever elements integral over a, they are actually elements of c. That shows that this x plus r minus y and x times y, they are actually members of c, Therefore, C is a subring, right? Yes. And this C we will call it as whatever we have defined here, which is a subring. This is called the integral closure of A in the given ring B. So this C is nothing but integral closure of A in B. Okay. So all the elements which are integral of elements of B which are integral over A are we are denoting by C. Okay. So there are two possibilities because your C, okay, is in between A and B. C may be equal to B, or C may be equal to A, or C may be in strictly between them also. Okay. So if at all C is equal to A, okay, if C is equal to A, then we say that this A is integrally closed in B. That means it is closed. You don't have any outside elements outside A which are integral over A. Okay. So then, so if whenever your C is equal to A, if C is equal to A, then we say that A is integrally closed. Okay, in B. And if C is equal to B, that means every element of B is integral over A. So in that case, we say that B is integral over A. Okay. So these are the two extreme cases. A is said to be integrally closed and B is integral over A. Now we'll see some transitive properties and other properties of integral this dependence. So if we take A, B, C, these are subrings. So remember this C is not this one. Now it is different. A, B, C and C are three rings, and if at all B is integral over A and C is also integral over B, okay, then if this is the case, then you can say that C is integral over A. Okay, and it is not at all difficult one. What we want to show is take an element, we want to show that it is integral over A. So that means it should satisfy some equation R by using the equivalent characterization. C of X is finitely generated over A. If we can prove that, it is fine. Okay. Because this, so we have started X is in C, but C is integral over B, so therefore this satisfies some equation with coefficients coming from B, and that is this one. Okay, x power n plus b1 x power n minus 1 plus bn is equal to 0, where bi's are coming from B. But now observe that these bi's are in B and B is integral over A. What is meaning of saying that? This implies when you adjoin A to this bi's, b1, b2 up to bn, this is finitely generated over A, right? If you call it this as b prime as this, therefore we got that b prime is finitely generated over A, right? And this x is satisfying the equation which is coming from b prime. So therefore you can write that x is integral over b prime, right? And b prime is finitely generated over A, and x is integral over b prime. That means b prime of x, okay, is finitely generated over A over b prime. Okay, and if you consider this, b prime is finitely generated. So if you consider these two statements, then transitivity you can apply. So what we get here is that b prime of x, okay, is finitely generated over A. That shows that, again using that result, this implies x is integral over A. X we started from C and we shown that it is integral over A. So therefore every element of C is integral. That shows that C is integral over A, right? Okay. So we have proved the transitivity property of this integral dependence. And some of the other corollaries from here, if you say that A is a subring of, if you consider A a subring of B and C, of course, which is the integral closure of A, okay, integral closure of A in B, then this is, you can say that this C is integrally closed, okay, in B, which is very, very clear. If you take any element which is integral over C, you show that it coming from C itself, and okay, that proof is not at all difficult. It is self-explanatory. What is another theorem is that when you have two rings, A is a subring of B, and suppose B is integral over A, then we can go to take some B. Okay, B is an ideal. So B is an ideal of the ring B, right? And you take contraction A, which is nothing but contraction of B. What is that? Intersection with A. Okay, this is called contraction. So you have an ideal here and correspondingly you have an ideal here, which is namely contraction. Then you go to their modulo, B modulo B. This will become integral over A modulo A. Okay, so whenever B is integral over A, and if you start with an ideal here, then B modulo B is integral over A modulo A, where this A is nothing but contraction of B. Okay, and another statement is, we know what is meant by multiplicatively closed set. So if you take multiplicatively closed subset of A, then S inverse B. Okay, if B is integral over A and S is a multiplicatively closed subset of A, then S inverse of B is integral over S inverse of A. Okay, proving things are not at all difficult one. If this is the first statement and this is second statement we want to prove, if at all we want to prove that this is integral over A, take an element. So we are taking with x plus b. Okay, we want to show that it satisfies some polynomial here. Okay, and that follows by using the fact that b is integral over A. So b is integral over A, that means if you take any element here which is integral over A, so because x is integral over A, we get an expression, right? Then by using the ideal properties and coset properties, we get this expression that shows that this x plus b is satisfying a polynomial over A modulo A. So therefore this one, right? Similarly, you can easily prove that S inverse B is integral over S inverse A. For that, you start with an element, okay, then use the fact that x is integral over A, you get an expression, then divide by suitable s power n and so on. So they are all basic calculations. I'll leave it to you, you can do it easy. Okay, the other interesting result here, this we use several times in this section, so that's why I say it is very important result. Take suppose A is a subring of B and both are integral domains. Okay, integral domains, and suppose B is integral over A at that time, then B is a field. Okay, if and only if A is a field. So whenever we have a situation, two integral domains are there and B is integral over A, then if one is field, the other one has to be a field. Okay, B is a field if and only if A is a field. Okay, again proof is not at all difficult, but it is straightforward. uh, Suppose assume that A is a field, then we want to show that this B is a field, right? So start with a non-zero element, y belongs to P, which is non-zero. We want to show that y inverse also belongs to P. So that will become then B will become a field, right? So how you do that? Because given fact that B is integral over A, therefore it satisfies some expression of this form where A is are coming from A. Then we can select this n in such a way that n is the smallest. By using the fact that they are integral domains, we can make sure that n is the smallest is possible. Then if once n is smallest, we can make sure that this an is non-zero. Okay, if an is 0, we get another smaller polynomial and so on. So an will become non-zero. We can do always that one. So therefore you divide by an inverse multiply and so on. So what you get is y inverse, which is this. So therefore this belongs to B because remaining all elements are coming from B only, right? Hence B will be a field. Similarly, suppose B is a field and x you take non-zero element, we want to show that x inverse is again in A. So write x inverse as linear combination of elements of A, that is this one. Okay, we are able to write x inverse as this, right? How we are using? Because x is in B and B is a field, so therefore x inverse is in B and B is integral over A. Use that fact and you get an expression in x inverse and simplify that. Okay, fine. Then the next one is you can say as a corollary which follows from here. So the understanding of the statement is important. So we have A here, okay, and you have B here. B is integral over A. Okay, so this B is integral over A, and we have now Q is a prime ideal. Okay, so Q is, this is a prime ideal of B, and P is nothing but contraction of Q. we know that this will also work, of course. So what is contraction of Q? Which is Q intersection with A, right? So you have a B, which is integral over A, and you have a prime ideal Q, and you have a contraction, you can call it as P here. Then if one of them is maximal, if and only if the other one is maximal, then Q is maximal if and only if P is maximal. So this result also we use several times. So whenever you have this situation, and if you know that any one of them is a maximal ideal, then we can conclude or claim that the other one is also a maximal ideal. Okay. Proof is simple. We have to go in this situation that if we have an integral over B is integral over A and B are integral domains, then if one of them is filled, the other one is also filled. Here we don't know whether B and A are integral domains or not. So we go one step further, and there we'll make sure that some of them are integral domains and integral over A and so on, right? So what is that one? Because Q is a prime ideal and P is contraction, so P is also prime ideal, right? So we have B, then you go modulo Q and A modulo P. Because both are prime ideals, what we know is that this is an integral domain, so both are integral domains. Okay, so here we can apply the previous results. Okay, so B over Q is integral over A over P. How that one? By previous result here. Yeah, sorry. Yes, here we proved that if we take any ideal and its contraction, then this modulo rings are integral over the other, right? So therefore, uh, here. So B over Q is integral over A over P because B is integral over A. Okay. So and this B over Q is integral over A modulo P. So therefore, if one of them is uh, therefore if one of them we know if this is a field, then this has to be field. So B over Q, when this will become a field, okay, so you can call it if and only if this Q is maximal, right? So Q is maximal, but B over Q is a field if and only if A over Q is a field, but A over Q is a field if and only if sorry, A over P, this is A over P, okay, if and only if P is maximal. So that is what we want to prove. Q is maximal if and only if P is maximal. Okay, right. So the idea is instead of playing with B over A, we are playing there B over Q over A over P, right? Fine. So what this result statement says is the most important one, which says that whenever you have B, which is integral over A, and if you have a prime ideal here, right, then you consider its contraction here, then Q is maximal, then P is maximal. If P is maximal, then Q is maximal. Okay, fine. Using this, we prove one more result, which is also interesting. You take A, P, A is a subring of B, okay, and P is integral over A, right? And take Q and Q prime, okay, which are prime ideals, okay, prime ideals here, such that Q contained in Q prime. Then suppose if their contractions, Q contraction is same as Q prime contraction, if you call it that as P, okay, if they are equal, then Q has to be equal to Q prime. So if you have two prime ideals in B, who of course one is contained, Q is contained in Q prime, whose contractions are same, then the original prime ideals, they have to be same. They cannot be two different prime ideals. Okay, so two different prime ideals cannot have same contraction here in this scenario. Okay, fine. How we'll do this is by taking for now onwards some 2-3 results. We go through this commutative diagram type. So you have A here, because A is contained in B as a subring, you have always this inclusion map. So this F is inclusion. Okay, that means sending every element to itself in B, right? Then you take this, because P is a prime ideal, so you take this local ring and you call it this as alpha. Similarly B to B P, okay, because you if you take this prime ideal, then you consider this P, okay, and we have from this one we have FP, okay, we have seen such results, right? And this diagram is commutative, okay, you can check that. If you go from, you start from A suppose, then go to B, and BP is same as from A to AP and AP to BP. So this is a commutative diagram. We use this one to get our result Q is equal to Q prime, okay. So what are our result element information we have? Q and Q prime are here, and P is prime here, ideal here, okay, which is nothing but contraction of Q and Q prime. We want to show that Q and Q prime are actually same, right? The idea is, remember here our S is A minus P, okay, and AP is a local ring with having one unique maximal ideal, okay. Fine. And this FP is S inverse of F is a map. Now what you we have P is a prime ideal here, right? P is a prime ideal, then you consider its extension, that you call it as M, that is extension of P, okay. Remember this AP has a unique maximal ideal, right? Now you take here n and n prime. So just like for P, we have considered its extension. Similarly for Q, you take which is n, and here also n prime. Okay. So what is this? N is nothing but Q extension. N prime is Q prime extension. Okay. Then n and n prime. Okay. Now this you have QE, Q prime E, and P, right? So what you can observe here is that by commutative of the above maps, so you take Q and you contraction here, okay, or you extend it here, then you contract, and you again contract it, it should be same. So that means QC, then you extend it. So Q is here, you contract it and you extend it, here you are coming, okay. So what is just like, you take Q, then you come here which is QC, then you come here which is QCE, right? This should be same as for Q, you take its extension QE, okay, then you contract it. These two should be equal because of commutative diagram. That is what we have written here. QCE is same as QEC, okay, but QE is nothing but N, so PE is NC. Similarly, P is N prime C, right? But our PE is M. You can see here. So therefore, M is equal to NC. Similarly, M is equal to N prime C, right? So therefore, M is N contraction, which is same as N prime contraction. Okay. Now you can observe that because Q is contained in Q prime, their extensions, okay, their extensions N is contained obviously in N prime, right? So N and N prime, they are here. So as M is a maximal ideal in AP and M is equal to this one, right? So therefore what you observe, N C and N prime C, right? They are equal. So therefore they are also maximal ideals, right? Now you are here, okay. So your N C and N prime C, they are actually equal. Not only that, they are maximal ideal. So therefore by using the previous result, because it is integral over this, one of them are maximal ideal, then the original is also maximal ideal. So therefore N and N prime, what we get here, they are also maximal ideals because their contraction is maximal, so they should be maximal here also. But the moment they are maximal ideals, they have to be equal. So N and N prime, we proved that they are actually maximal ideal and they are equal, okay. Now use the one-to-one correspondence also, by because P intersection S is empty, you can observe that Q intersection S and Q prime intersection S is also empty. So there is a one-to-one correspondence between prime ideals in S inverse Q and prime ideals in B. Okay, what is that? There is a one-to-one correspondence between S inverse Q and Q if S intersection Q is empty. Okay, so using that fact, if you take this why Q and Q prime are equal, because this beta inverse of n and beta inverse of n prime, because n and n prime are same, so they should be equal to equal. but this is nothing but q and this is nothing but q prime. So we get that q is equal to q prime, right? Yes. So we have proved that if we have two prime ideals q and q prime such that q is contained in q prime, okay, and if their contraction is same, then they should be same, they cannot be different, right? Yes, using this now we prove another interesting result, which says that again you take a and b which is integral over a. Now this time we are taking a p is a prime ideal here, okay. If p is a prime ideal, then there exists a prime ideal q here, such that its contraction is this, such that q intersection a is nothing but p. So what this result says, whenever we have b which is integral over a and a prime ideal in a, then there always exists a prime ideal in b whose contraction is this p, okay. Again the idea is using these commutative diagrams, a is sits b inclusion, then you consider this local ring ap bp we have here, you can call it this is alpha, this is beta, this is f and fp, okay. Then this diagram is a commutative diagram, right? What we have here is, see, suppose you take, because it's a local ring, you have a maximal ideal, right? So you can call it, say suppose that is n is the maximal ideal, unique maximal ideal. Then you take its contraction, which is n intersection ap, you can call it this as m, because this is a maximal ideal here, so therefore this has to be a maximal ideal, so we got that m is maximal ideal here, right? And because of AP local ring, this has to be the only maximal ideal, we cannot have any other maximal ideal, right? Now the obvious thing is you take its contraction, okay, m contraction, that we know that it has to be p, right? And you take its contraction here, okay, n contraction or beta inverse of n, okay, that you call it as q beta inverse of this n. Then you take its contraction, that is the idea, okay. So because of commutativity, see, you have here, then you have contracted this m is coming from this, right? So n, then you contract it, again you contract it, is same as for n you go to this contraction, this contraction, right? So one way you get p, the other way you get q and q contraction. So what we have proved is q contraction is p, right? So everything we play with these diagrams and in detail we have written here, you can go through it, right? We end up this with an important result called going up theorem. What going up theorem says is that if you have b again is integral, okay, over a, if you have prime ideals p1, okay, p2, p3 and so on here in a, okay, of chain of prime ideals, and suppose you have q1 q2, okay, qm here up to pn, suppose where m is strictly less than n, okay, where these qi's are nothing but contractions of this pi's, that means qi intersection a is pi for I is equal to 1 to m, then this we can extend up to qn such that each qi is a contraction of pi. So that's why we can say going up theorem, that means here we can go, we can have this chain can be extended further to get prime ideals which are whose contractions are nothing but this original pn's, okay, right? So you have p1 pn and you have q1 qm, okay, such that where m is strictly less than n, qi intersection a is pi for I is equal to 1 to m, then there exists qm plus 1 up to qn, okay. For that chain you can write here if you want, right? Such that qi intersection a is pi for all I from this time 1 to n, okay. So how we do this one is we'll do it just like in type of induction. So we'll take m is 1 and of course m should be strictly less than n, so n we will take it as 2. So what is the meaning of that? So we'll write that first here. That means we have a here and b, we have two prime ideals P1 and P2. Of course, P1 is contained in P2, and you have a prime ideal Q1 such that Q1 intersection A is P1, and we will prove that there exists Q2, okay, such that Q2 intersection A is P2. This should be our claim, right? How we do? By using the previous result. What previous result says? Whenever you have a prime ideal here, then there exists a prime ideal, okay, whose contraction is this and so on, right? But instead of doing for A and B, we do it slightly because we require integral domain and so on. Okay, so what we do, instead of applying for A and B, we go for A bar, which is A modulo P1, and B bar, which is B modulo Q1. So therefore, and B is integral over A, so therefore this A bar and B bar is integral over A. Okay, right? Fine. Then P2 is a prime ideal in, what you get here is P2 contains P1, so therefore P2 will become P2 bar, if you call it, which is P2 upon P1. This is a prime ideal, so P2 bar, which is P2 upon P1, is a prime ideal. So this, let me write here. So we are in this situation now. A bar is contained in B bar, and B bar is integral over A bar. So here we will apply the previous result, which says that P2 bar, which is nothing but P2 upon P1, this is a prime ideal in A bar. Okay, so what you will get? This implies there exists a prime ideal, you can call it Q2, okay, or you can call it Q2 bar in B bar, okay, which is nothing but B upon Q1, such that the contraction of Q2 bar contraction, that means Q2 bar intersection A bar, is nothing but that P2 bar. Okay, so what we have applied is this result. Yeah, that's why this is interesting. Whenever you have B integral over A and P is a prime ideal in A, then there exists a prime ideal in B whose contraction is this, right? Okay, so you can see that we got a prime ideal Q2 bar, which is nothing but something upon Q1, so you can call it Q2, which contains Q1, right? Then it is easy to show that Q2 intersection A is P2, right? And that is follows from this one. P2 is equal to Q2 intersection A by using this commutative diagram. Okay, for A, instead of AP, BP, we are applying for A bar, B bar. Okay, that modulo one, right? Now, applying induction hypothesis, we get the other one. That means assume that the induction hypothesis is true for n minus 1. Then, because Pn minus 1 is contained in Pn and Qn minus 1 intersection A is Pn minus 1. So, by taking that A, then B here, okay, then here instead of taking that bar, you take this related to this. That means A modulo Pn, and here you take B modulo this Pn minus 1 here, and Qn minus 1. Then you apply that and you will get that there exists a prime ideal Qn such that Qn intersection A is Pn. Okay, that proves that going up theorem, right? And we'll stop here. Next class we'll see some other results.